Hi, this is the second part of section 3.2. We're going to take a look at what I'm calling at least problems. The phrase at least is going to show up in these problems, and that's how you know that this is the technique you're going to use. If you look at the example that I have up, we have 50 people, 23 of them like basketball. What's the probability that I choose 3 people with replacement and at least one likes basketball? So I've kind of mapped out the options so you can see if I'm going to choose 3 people, here's all the ways that this can happen. I'm using Y for yes and N for no. So yes, I like basketball, or no, I don't. The first option here is all of them say yes. That's one way that I could select 3 people. Or the first person could say no and the next 2 could say yes. Or the first one could say yes, the next one's no, and the next one's yes. So what I have written out is all the different permutations. That's a math word that means all the orders or the combinations or the ways that this can happen. So what I want you to do is look at this list and decide how many of these have at least one liking basketball. Let's circle them. Well, all 3 liking is at least one. At least means 1 or more. So that's 1 or more. Any option where I have 2 yeses is 1 or more. So all of these are options. And then any option where I have 1 is also at least, because 1 counts as at least 1. So as you can see, there's only one option that doesn't count. That's if I choose 3 people and all of them are no's. Now, the problem with this, and the thing that makes these difficult, is that when I want to know what's the probability that at least one likes basketball, I have to deal with all of the ones that have a yes in them, and there are a lot. There's 4, 5, 6, there's 7 options. And I have to calculate the probability of all 7 of those options and combine them, which is a difficult problem. Now, another way to approach this is using the idea of complements. So let's talk about how we talked about whole and like dividing a whole into parts. That's what a complement is, right? Like, remember we talked about if it rains and it doesn't rain. Those add up to be the whole 100%. So if I draw a circle around all of these options, and that represents all of my options, 100% of my options, I could divide these options into sections. 2 sections. One is the section that has all of the no's, and the other is anybody who has the yeses. And these together make up 100% or the whole. So if I want to know what's the probability of this orange section, all the ones that have a yes, it is equivalent to take the whole and subtract just the no options. So I have this colored. I have all the yeses in orange, and I have all the no's, the no's in pink. So the probability of at least one yes, that's all my orange options, is equal to 1 minus the probability of all no's. Now think about that. 1 represents the whole. That's 100% in my decimals. And the probability of all no's is the part that I don't want. So that's why I'm subtracting it off. So if you think about this circle, I've got the whole circle. That's 1. And then I subtract off this option of just all no's. What I'm left with is all the orange options, which are all at least 1. Now, why does that make it easier? Because the probability of all no's is just a simple and problem. What's the probability that somebody doesn't like, and doesn't like? Okay. So let's go into this. 1 minus. Now, if I want all no's, I've got 3 events. I'm building an and problem. So I want no, no, no. I'm going to have 3 events. I'm going to multiply them all together. And I have to figure out what's the probability that this first person that I draw does not like basketball. Now, this is confusing because I know that it's asking for somebody who does like it, but what we're doing is we're subtracting off the option that doesn't work, which is all of them don't like it. So that's why we're changing that language. So if the problem tells me that 23 like basketball, that means that 30, 40, 50, 27 of them don't like basketball. So let's look at that. There's 50 total. 23 like basketball. That means 27 don't like basketball. And that adds up to your total of 50. So what's the probability that I get somebody that doesn't like basketball? 27 out of 50. Now, with replacement means I'm putting that person back into the pile. These are independent events, and I'm not going to change my total out. So I'm going to go 27 out of 50 is the chances for my second person not liking, and 27 out of 50 is my chances for the third person not liking. Then I can enter all of those into a calculator and figure it out. Let's go over to the calculator. We've got 27 over 50. So I'm going to go 1 minus 27 out of 50 times 27 out of 50 times 27 out of 50. And I get 0.84. Now, so there's an 84% chance that I select somebody that likes basketball. This is equivalent as if I had added up all of these different options for probabilities for at least one person saying yes. So the formula for these at least problems, the way that you do them is you do 1 minus the probability of the complement. Remember that math word means the opposite of what it's asking for. So if I want at least one who likes, I'm going to go 1 minus the probability that they all don't like. That's the complement of it. All right, that's how it looks if you're building fractions. Let's look at it if it's already in decimal form. So let's say the probability that I randomly select a cat owner is 30%. What's the probability that I select 4 people and at least one owns a cat? So again, this keyword of at least, what that means is that I'm going to do 1 minus the probability of the complement. So what's the complement of owning a cat? It's not owning a cat. So I want 1 minus the probability of not owning cat. And the number of people that I select, which is 4, dictates how many events I have and how many things I multiply together. So my formula looks like this: 1 minus, and I've got 4 things that I'm going to multiply that I have to fill in. Now, when your probability is given to you as a percent or a decimal, then we don't worry about replacement or not, because this is it's implied that this is based on a population, and the numbers are so big that it doesn't actually matter. If you're subtracting 1 from a million, it doesn't change the value. So we just go ahead and use that 30% as it is and don't subtract 1 from it. If you're building fractions, if they're smaller numbers, then you do worry about that, but with percentages, you don't. So if I have 100% is my total, and I have 30% own cats, then that means that 70% don't own cats. So if I want the probability of not owning a cat, that's going to be 0.7. So I'm going to go 1 minus 0.7 times 0.7 times 0.7 times 0.7. And that's going to be the probability that at least one person owns a cat. Now on your calculator, you can come over here, and the quick way to do this is you put 0.7 and then you tap and hold on this squared button right up here. That'll give you, this is a to the n, that's a power. And what the power indicates is how many of these are there. So we said we were going to select 4 people. So that gives you 4 of those 0.7s multiplied together. So my answer here you can see is 0.7599. So we'll call that 0.76. Now why are these probabilities high? Well, because at least gives me a lot of latitude. I only need at least one cat. It's not like the card situation where I'm like, I want 4 queens. That's a very prescriptive hand that lowers your probability, but at least actually opens up the options. It's like, well, you could have 1 or 2 or 3. So there's a lot of ways that that can happen. And so these probabilities tend to be bigger, and the and probabilities tend to be smaller. It's one way to kind of gauge if your answer is correct or not. If you're doing an at least problem and you get like, 0.15, 15%, you might have done it wrong. You might have not taken the complement. By accident, maybe you did what it was asking for instead of the complement. So take a look at that. But if it's a straight and problem, your answers are probably going to be smaller percentages. All right, try some of those, and I will see you for 3-3 next time.